Hey guys, what's going on? In this video, I'm going to be talking about quadratic equations. If you've taken Algebra 1 or Algebra 2, you've probably seen these before. When solving quadratic equations, you're basically just solving for the x-intercepts. Here are the different forms of the quadratic equations. Here's standard form, here's intercept form, here's vertex form, and here's the quadratic formula. While you may have used each of these forms in one way or another, I'm going to attempt to prove to you that the quadratic formula is just a standard form written in a different way. Let's do some math together. My goal in the rest of this video is to help you understand that this thing over here is equivalent to this thing over here. Let's give it a go. I'm going to start here by writing our equation in standard form. We have ax squared plus bx plus c is equal to 0. Then I'm going to subtract c from both sides. From that, we're going to get ax squared plus bx is equal to negative c. If this first step seems familiar to you, it's because we're going to try to complete the square now. To complete the square, this first term must be a perfect square. Since there's no way of guaranteeing that a is a perfect square, we need to get rid of it. To get rid of the a, we're going to divide both sides of the equation by it. Rewritten, we're going to have ax squared over a plus bx over a is equal to negative c over a. These a's in the first term are going to cancel out. A little bit more simplified, I'm going to write x squared plus bx over a is equal to negative c over a. The reason why I left some space is because we need to complete the square. Here's an easier example to remind you how to complete the square. To complete the square, you always take half of the b value and then you square it. In this case, b would be 6, so we would take half of 6 and then square it. Half of 6 is just going to be 3, and 3 squared is going to equal 9. To complete the square here, we would add 9 on both sides of this equation. This bx over a can be rewritten as b over a x. I know it's a little strange, but this b over a is our coefficient of x, which is typically our b value. Remember that to complete the square, we have to take half of b and then square it. When taking half of b over a, that's just going to be b over 2a. After taking half, we're just going to square it now. Whenever we have a fraction squared, we can write it as the numerator squared over the denominator squared. The numerator here is just going to be b squared, and the denominator is going to be 4a squared. This expression here will complete the square. Let's now write it into our equation on both sides. Finally, we've completed the square. We've now added the exact value we needed to complete the square and make a perfect square trinomial. Here are some examples of less scary looking perfect square trinomials. Notice how the first and last terms are always perfect squares, and when they're factored, their square roots are in the binomials. The square root of x squared is going to be x, and the square root of b squared over 4a squared is going to be b over 2a. We're going to have 2 of these here. This is still equal to negative c over a plus b squared over 4a squared. Now that we've factored it, let's simplify it a bit more. Since we have 2 identical binomials here, we can write x plus b over 2a squared is equal to negative c over a plus b squared over 4a squared. The whole point was to get these x's in 2 locations to just having x in 1 location. Now let's focus on simplifying the right side. We need to rewrite the right side as one fraction. To do that, we're going to need to find the LCD, or least common denominator. Since this a here is a factor of 4a squared, the LCD is just going to be 4a squared. To get that fraction on the left to have that denominator, we're going to have to multiply it by 4a over 4a. We can leave the fraction to the right because it already has a denominator of 4a squared. Multiplying, we're going to get negative 4ac over 4a squared plus b squared over 4a squared. Now that we have common denominators, we can rewrite this as one fraction and write negative 4ac plus b squared all over 4a squared. Using the commutative property, we can rewrite our numerator as b squared minus 4ac and write that over 4a squared. We're turning the numerator around so it looks more like the quadratic formula. Now let's take our one fraction and swap it back in. The left side's still going to be the same with x plus b over 2a squared. And the right side's going to be b squared minus 4ac on top and 4a squared on bottom. Now to get this x alone, we need to get rid of the exponent of 2. We can do that by taking the square root of both sides of this equation. Continuing this up here, the left side is just going to be x plus b over 2a and we can write the right side as the square root of b squared minus 4ac all over the square root of 4a squared. Just a reminder, when you're taking the square root of fractions, you're always allowed to separate the radical into the numerator and the denominator. The square root of 4/9 would simply be 2/3. On the left side, we still have x plus b over 2a. The numerator to the right is going to be plus or minus the square root of b squared minus 4ac. And since the denominator is a perfect square, we're going to get 2a. Finally, to get this x completely alone, we can subtract b over 2a from both sides. After subtracting, the left side's just going to have x alone, and the right side is going to be negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And since these denominators match, we can rewrite this as one fraction. After all that work, we can finally write x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And there we have it. I hope I somewhat convinced you that the quadratic formula is really just the quadratic equation in standard form, written in a different way. If you like this video, please give it a thumbs up and let me know in the comments section below. Keep up the good work, and I'll see you next time.